there, and welcome. Today, we're pulling back the curtain on one of the most important, but maybe one of the most invisible fields in all of tech: systems engineering. You know, it's really the secret sauce behind just about everything, from the phone in your hand to the rovers on Mars. So, how does it actually turn these impossible ideas into reality?
Okay, let's start with a scenario. Let's say we're building a brand new satellite. The whole mission? To image the Earth like never before. And your electronics team, they are absolutely fired up. They want to use the most powerful, most advanced sensors that have ever been created.
And right behind them is the software team. They're pushing to pack the satellite with the latest and greatest AI, so it can process all those images right there, in space, in real time. I mean, this is totally cutting-edge stuff.
Meanwhile, the structures team gets their assignment. And it's a tough one. Make the entire satellite incredibly tiny, something you could almost hold in the palm of your hand. Why? Well, every gram you launch into space costs a fortune, so smaller is better.
So, you've got all these brilliant people, right? Each with an amazing vision for their part of the project. But then, the power team runs the numbers, and they come back with some bad news. To power those amazing sensors and that supercomputer AI inside that tiny box, you would literally need solar panels stretching across the entire solar system. Okay, so now what happens? What do you do when all these brilliant competing ideas crash into each other?
Well, how do you possibly bring order to this creative chaos and find a path forward that, actually works? The answer, my friend, is systems engineering. It's the master plan that turns a pile of conflicting parts into one single successful machine.
Now, if you want the formal definition, groups like INCOSE and NASA call it an interdisciplinary approach. But what that really means is getting all the different experts, the electronics folks, the software gurus, the structures people in the same room from day one. It's about making sure that the final product, from the very first concept all the way to its final day in orbit, actually does what you need it to do.
But you know what? I think a user on Reddit put it perfectly. They said it's kind of like a mix between an engineer and a project manager, but one who is laser focused on all the technical stuff. Think of the systems engineer as the project's technical conductor, making sure every single part of the orchestra is playing the same song perfectly in tune.
So how in the world do they conduct this orchestra? Well, one of their most powerful tools is a deceptively simple diagram. It's called the V-chart. The V-chart is basically the roadmap for the entire project. As you go down the left side of the V, you're breaking the big idea down, logically. You're decomposing the system into smaller and smaller, more manageable parts. Then, once you hit the bottom, you start moving up the right side, where you physically start building it all back up.
So here's how it works. You start at the top left with a big picture, the mission concept. Then you move down the V, breaking that concept down into subsystems and eventually into individual components. And for each tiny piece, you write a clear requirement. Once everything is designed, you start climbing up the right side. You physically integrate or assemble all the pieces. Then come two of the most important steps of all: verification and validation. Verification asks the question, did we build the part correctly? You test each piece to see if it meets its specific requirement. But validation, that asks a much bigger question. Did we build the right part? That's when you test the fully assembled system to prove it actually achieves the original mission.
So that's the process, the big picture. But what does a systems engineer, someone like Farah Ali-Bai at JPL working on the Mars Perseverance rover, actually do all day? Well, to make a mission like that succeed, they have a whole toolkit they rely on. They're the ones writing those crystal clear requirements, these shall statements that say exactly what every single component has to do. They manage the interfaces, acting as the glue between teams to make sure the power board actually plugs into the main computer correctly. They run what are called trade studies, where they analyze all the options to find the absolute best balance between performance, cost, and risk. And maybe most importantly, they are the relentless guardians of the project's technical budgets, and they are always, always thinking about risk. And let's look at a really critical example of a technical budget, the mass budget. This table shows just one tiny piece of it. See, on a space mission, every single gram costs a ton of money to launch. The systems engineer's job is to give each team a strict mass allowance and then track it with incredible detail, making sure the grand total doesn't go over what the rocket can actually carry.
Okay, so when you put all of this together, the master plan, that V-chart, the daily toolkit, you get something more than just a cool piece of technology that works.
You get a repeatable blueprint for achieving success.
This, right here, is the hidden discipline that lets us build unbelievably complex things like the Space Shuttle or the Mars rovers. It's the process that stops you from making hugely expensive mistakes down the road. And it ensures that when all those thousands of pieces finally come together, they create a true marvel of technology that actually does its job.
As former NASA Administrator Michael Griffin put it, it really is both an art and a science. It's all about balancing those tough trade-offs and compromises to create a single, coherent system, one that isn't dominated by any one team's pet feature, but instead serves the overall mission above everything else.
So look, if there's one thing you should take away from all this, it's that systems engineering is the science of mastering complexity. And as our ambitions get bigger and our technology gets more complex, from building sustainable cities to exploring other planets, this is the skill that will turn our wildest visions into reality. It just makes you wonder, right? What impossible problem is it going to solve next?